Hello everyone, it's a pleasure once again to welcome you all to this second semester course on Inferential Discrete Mathematics under the BCA online learning program. Today we'll move forward and discuss the fundamental types of a function that can be defined between any two non-empty sets. We'll have a look at four main types. We'll have a look at some examples which classify these types, and we'll also solve a couple of problems. The first major type that we'll discuss is the one that we call as a one-to-one function. If f denotes any function between two non-empty sets, non-empty sets x and y, we call that function as a one-to-one function. We call that function as a one-to-one function if distinct elements from the set x are mapped to distinct elements in the set y. In other words, if every element of the set x has a unique image in y, then we call the function as a one-to-one function. The same function also goes by the name of an injective function or an injection. For an example, we can consider two sets x and y. If I can define a function like this, mapping all elements of x to an element of y, you will see that their images are unique. 2 is mapped with 1, and this 1 is not the image of any other element in x. 4 is mapped to 2, 6 is mapped to 4, and 8 is mapped to 3. All the images here are different, they are unique. For any element in x, the image is a unique image. Such a function is what you call as a one-to-one function or a bijection or an injection. The second type that we will discuss is a non-two function. A function f from x to y is called a non-two function or a surjective function if the range of the function is the same as the codomain of the function. You can recall the definition behind the range. The range of the given function is the set of all images of all elements in x. Let x contain 5 elements and let each of them have an image in the set y. Whatever image that you have, you collect them and put inside a box. That box is what you call as the range. Now we classify a function to be a non-two function if the range of the function is the same as the codomain. Such a function is what you call as a on-two function or a surjective function. That is another name that goes by it. You can also call it as a surjective function. The other way to look at this is every element in the set y, which we refer to as the codomain, has a definite pre-image in the set x. For an example, let's draw another pictorial representation of the same. This function talks about the pairing up of elements in this manner. 2 and 2 are together, 4 is mapped to 1, 6 is mapped to 3, 8 is mapped to 4. This is the set of all ordered pairs that represent the given function. Here you see all elements in the set y have a definite pre-image in the set x, and therefore this function qualifies to be a non-two function. Now suppose I include another element, say 5, in the set y, then you see that this element 5 is not mapped with any of these 4 elements in set x. Such a function will not qualify as an on-two function. Such a function is not on-two because not every element in the set y has a definite pre-image. the range is not equal to the codomain. There is one element in the codomain which is not present in the range. Hence, we cannot call this as an onto function. But had it not been for this element 5, then we can say with conviction that the given function is actually an onto function. And there are also some functions which are both one-to-one and onto. We call them by a special name called as a bijection. It's both of them. Functions which are both one-to-one onto, we call them as a bijection. It is both an injective function and a surjective function. Therefore, it gets called as a bijective function or a bijection. Example of this can be given like this. Let's take two sets x and y. I'll give you one example of for each of the three cases here. Case 1, let's take the same set. Third example will be on a bijection here on your screens, where we are having a look at these arrow diagrams, and let's find out if they are bijections. Now, if you look at the far right corner, this function from x to y, where 2 goes to 1, 4 goes to 2, 6 goes to 3 and 8 goes to 4, you will see that this element 5 does not have a pre-image, a defined pre-image in the set x. So, this is not onto. Some textbooks also call such functions as into functions, where one such element gets missed out. It is not part of the set of all images. So, it is not onto, but it is still one-to-one, because every element has a unique image in the set y, and hence you cannot call this as a bijection. But let us go to the next example, where 2 goes to 2, 4 goes to 1, 6 and 8 both go to 3. You will see that the element 3 is the image for two different elements 6 and 8, and therefore the images of the elements 6 and 8 are not unique, they are the same. Hence, this is not one-to-one. Some textbooks also call this as a many-to-one function. More than one element gets mapped to the same element of set y. And this is also not onto, because you will see that the element 4 is missed out. It's neither one-to-one nor onto. Look at the one on the left, the far left corner. You will see that every element of the set y has a pre-image. The element 2 goes to 2, 1 goes to 4, 3 goes to 6 and 4 goes to 8. So, this is in fact an onto function. This is also a one-to-one function. Therefore, you can call it as a bijection. That's the extra name you can give it. Okay. The next is a very easy function to understand. It's called the identity function. You call this as the identity function. It's called the identity function here. A function I from a set x to itself is called an identity function if every element is mapped onto itself. Here you will not have two different sets getting called as domain and codomain. It's a function from a set to itself. So, both are the same. X goes to x again, but 1 goes to 1, 2 goes to 2, 3 goes to 3 and 4 goes to 4. Such a function is what you call as the identity function, where every element gets mapped to itself. It's like looking in front of a mirror. The object is reflected. The image and the object are one and the same. Such a function is what you call as an identity function. Okay. Now, we will also have a look at one more way to combine two functions. We had a look at such a combination when we discussed relations also, where we studied the composition of two relations. Here we can extend the same idea to the concept of functions. We can also understand how to find the composition of two functions. Now if f and g are two functions, then you can find the composition of one on the other. It's called the G composition f is defined in this form. So it's like this. Give you an example. Let's consider three different sets x, y and z. Let's first define set x. Now let's define the function f like this. This is about f. And let's define function g. Let this be about g. Now how do you define the composition of the function g of f of x? Now g of f of x is what you call as the composition, and this is how it is defined. G of f of 1. You know that f of 1 is b. So what is g of f of 1? Is same as g of b, and g of b is actually 4. And g of f of 2 goes to a, so this is same as g of a, and a goes to 5. And g of f of 3 goes to c, so the answer you are looking for is g of c, and that is 6. So now you will see that as a composition mapping, you can realize that 1 is getting mapped to 4, 2 is getting mapped to 5, and 3 is getting mapped to 6. Such a method of combining two functions is what you call as the composition of two functions. Yes. And the next one is about the inverse of a particular function. Now let's consider that there are two functions, f from x to y and g from y to x. Then you call the function g as the inverse of f if both these are identity mappings. Further, you can define the inverse of a function. Let's say this is set x, this is set y. Let's have x defined in this manner and y defined in this manner. I'll denote x to y, the function f, in black, and the function y to x as the function in red. So this is a way to find a function and its inverse. If this is what you have, then we can define the inverse of any given function. For a simpler example, we can also consider any polynomial function which is linear. Then you will have an inverse function easily defined. Let's define one function f from the set of integers to the same set. Let me define f of x as 2 plus x, and z is a set of all integers, so you have both positive and negative integers. I'll just selectively pick a few of them. Z, the domain is set of all even integers, and the codomain is also set of all even integers. So you'll have these elements as part of your set. Now when I define the function, I say f of x is 2x, so f of minus 6 is minus 4, f of minus 4 is minus 2, f of minus 2 is 0, f of 0 is 2, f of 2 is 4, f of 4 is 6, and f of 6 is 8, so on and so forth I can define. So the arrows will just go down by one step and you can have the functions defined in this manner. So if this is the case, I can define another function g of x, this time between the same sets again, but I'll define my image like this. G of x is x minus 2. So g of minus 4 is minus 4 minus 2, that's minus 6. G of minus 2 is minus 2 minus 2, that's minus 4. G of 0 is 0 minus 2, that is minus 2. G of 2 is 0. G of 4 is 2. And g of 6 is 4. So whatever went from x to y can be brought back to x. 6 goes to 4, 4 goes to 2, 2 goes to 0, 0 goes to minus 2, 2 goes to minus 4 again, minus 4 goes to minus 6 again. So an element from x will have a definite element as an image in y, and with that you can define the inverse of the actual function. Such a function is what you call the inverse of the given function. And it is better to note the fact that a function can have an inverse only if it is also a bijection. Unless it is a bijection, you cannot define the inverse for a given function. In other words, any function that is both 1 to 1 and on 2 will always have its own inverse function defined. With these definitions, let's have a look at a couple of examples that will help us understand these ideas in a better manner. What you have is a set of functions f and g defined between the sets a and b, and that's how they are defined. Now we'll have a look at these functions and let's try and classify them into the types that we just saw. A is 1, 2, 3, 4, 5. B is 1, 2, 3, 8 and 6. The function maps 1 to 8, 3 to 6, 2 to 1, 4 to 3 and 5 to 2. How can we classify this function? Can we classify this function as a 1-to-1 function? Yes, because if you write the set of all images, 1 goes to 1, 1 goes to 8, 3 goes to 6, 4 goes to 3, 2 goes to 1 and 5 goes to 2. All these images are unique, and therefore this function is an injective function, and that is a 1-to-1 function. Now can we call this as an onto function? Now recall that a function becomes the extra, it has the extra status as an onto function if its range and the codomain are the same. The range of the given function is these 5 elements, 1, 2, 3, 6 and 8, and they are the same as the codomain in the set B. So you see that the range of the function is the same as its codomain, and therefore it is also a onto function. It's an onto function. It is also an 1-to-1 function. Therefore it's both an injective function as well as a surjective function. Therefore you can see that the function f is actually a bijection. The function f is a bijection. Let's discuss the second example now. Let's talk about g. G also defines a function from a to b. And how are we defining g? G maps 1 with 1, 2 with 2, 3 with 3. But can we call it as an identity function? Of course you cannot. 4 doesn't get mapped to 4. 4 gets mapped to 8. So since they are not the same, since 4 is not mapped to itself, we cannot call it as an identity mapping. 5 is also mapped to 8. Now what else can you attribute this function to be? you can see that this function is clearly not 1 to 1. In fact, it is many to 1 because both 4 and 5 are getting mapped to the same element called 8. And what about the onto nature? Can you call it as a surjective function? No, you cannot, because the element 6 is not mapped with any of the 5 elements in the set X. Therefore, it's not 1 to 1, not onto. So it's neither 1 to 1 nor onto. And we also saw that it cannot be an identity function. And since it is not 1 to 1 and also not onto, we cannot define the inverse of the given function. One more example. We have 1, 2, 4 and 5 as the domain, 1, 2, 3, 6 and 8 as the codomain, and we have two functions defined. One is f and the other is g. Let's see if you can classify these two functions once again. 1 goes to 8, 4 goes to 3, 2 goes to 1, 5 goes to 2. Can we call this as a 1 to 1 function? It turns out to be yes. Yes, you can in fact call this 1 to 1 because you write down the images, no image occurs twice. You have only these numbers 1, 2, 3 and 8 getting counted as images, and none of them occurs twice. Each of them occurs exactly once. Therefore, f is actually a 1 to 1 function. But can we call this as an onto function? Unfortunately, you cannot, because once again you see that the element 6 is missed out. The element 6 is not mapped with any element from the set A, and therefore it is 1 to 1, but it is not onto. Okay, what about the next one? 1 goes to 1, 2 goes to 8, 4 goes to 3, 5 goes to 8 again. What is different this time? Here again you will see that it is neither 1 to 1 not onto. Not 1 to 1 not onto. Because both 5 and 2 are getting mapped to the same element 2, and once again 6 is missed out. Therefore, it's neither 1 to 1 nor onto, and obviously it is not a bijection. You cannot define an inverse function also. Now let's try a few more problems for you to get yourselves comfortable with the idea of functions. We have two sets A 1 through 5 and B 2 through 10, 2, 4, 6, 8 and 10. Now can you classify F now? F talks about the element 1 getting mapped to 8, 3 getting mapped to 6, 4 getting mapped to 2, 2 getting mapped to 4 and 5 getting mapped to 10. One thing that you can obviously find out is that these images are unique. Therefore, the function is a 1 to 1 function and no element is missed out, which means the function is onto also. Every element in the set B also has a pre-image in set A. Therefore, it also qualifies to be an onto function. It is also 1 to 1. Therefore, the function f is a bijection. The function f is a bijection. One goes to 10, 2 goes to 4, 3 goes to 6, 4 goes to 2 and 5 goes to 8. You will see that this is also an example for a bijection. So both f and g turn out to be bijections. We'll have a look at one more example, the final example of today's class. One to 8, 3 to 6, 4 to 2 and 2 to 10. it's obvious that this mapping is both 1 to 1 and on 2. So you have a bijection. The second mapping G is 1, 2, 3 and 4, they get mapped to 10, 6 and 2 and 8. You will see that both 1 and 2 get mapped to 10, 3 gets mapped to 6, 4 gets mapped to 2, 8, the element 8 is missed out. Therefore, this mapping cannot be an onto function. This is not an onto function, but it is clearly it is also not a one-to-one function, because both 1 and 2 get mapped to the same element 10 of set B. Therefore, it can only be a many to one function.